Next speaker for our session 4 is Haemyeong Jung, method of seismic anisotropy produced by serpentine wedge.
Okay, thank you, Seismic. Well, welcome to Jeju Island. My name is Haemyeong Jung from Seoul National University. This picture shows the view of large serpentine body in the Monviso Italian Alps. I'm going to talk about today seismic anisotropy produced by serpentine in the Mantle wedge. Okay. I will first introduce you briefly seismic anisotropy in the Mantle wedge, and then talk about the previous studies on serpentine fabrics, and then show you petrofabrics of serpentine and tigorite in two localities, in Belmalenco and in Punta Vetolena in Italy. And then show you the result of seismic anisotropy produced by serpentine, and then talk about implications and summarize. Seismic anisotropy has been observed worldwide, as you see here, Alaska, Aleutian, Japan, Mariana Tonga, as well as Middle America and South America. When shear waves propagates into anisotropic medium, then it is split into two. So you can see here the polarization direction of a fast shear wave. This can be detected by the seismologists, and also delay time they can detect, so that this shear wave splitting can be used to show seismic anisotropy. Then this is an example showing seismic anisotropy in Tonga, Fiji subduction zone. Pacific plate subducts down. The black color shows trench. The red bars shows the polarization direction of a fast shear wave, showing here nearly trench parallel seismic anisotropy. What causes this trench parallel seismic anisotropy? There are some models proposed. First thing is hydrous olivine having a B-type fabric may explain this feature. And also trench parallel flow, some people suggest. And then recently also hydrous faulting due to bending subducting slab. Another thing is that yesterday we also saw that the 3D mantle flow maybe also can explain this. Today we're going to focus mostly on the cold fore-arc mantle wedge. There are some seismological observations showing S-ray velocity perturbations under this central Cascadia. Here you can see the perturbation of. There are very low temperature, and then postdoctoral suggest that there are serpentinized fore-arc mantle wedge existing. In tigorite, the serpentine has a large stability field. As you can see here, the pressure up to 7 GPa, depending on temperature though, temperature up to 700 degrees C. This morning, Kokiso-san showed those similar features. There are serpentine existing here in the subducting slab, and also in the mantle wedge, cold mantle wedge, and also in between the place here in between mantle wedge and the slab. Serpentine is elastically anisotropic. Depending on orientation of serpentine, we have a P-wave velocity anisotropy up to 46%, and S-wave up to 66%. This picture shows antigonite, shown in blue color here. If serpentine deformed in nature, if they have a preferred orientation, then it will cause large seismic anisotropy. There was a nice initial study on the serpentine fabrics by conducting high pressure, high temperature experiment. Pressure was at 1 gigapascal, 30 kilometer depth pressure. Temperature was 300 degrees C and also 400 degrees C. X shows the shear direction. S is the shear plane. They observed that 001 axis is aligning subnormal to the shear plane. And 100 axis is aligning parallel to the shear direction. And then they proposed that transparallel seismic anisotropy can be explained using this fabric only if the subduction angle here greater than 45 degrees. There are also some studies on natural fabrics recently reported. And then here, Soda and Takaki looked at serpentine fabric in the Sakanosaki Peninsula in Japan. If you see here, the 001 axis is aligning subnormal to foliation, which is consistent with the experimental fabric. However, 010 axis is aligning parallel to lineation, which is different from experimental fabric. There are some other studies having similar fabrics here in natural fabric by Hirauchi et al. So I wanted to look at some more serpentine fabrics in nature and then think about the seismic anisotropy produced by this serpentine fabric. I collected samples from two localities, one from Punta Retolina, northwestern part of Italy. The other one is northern Italy, the Val Molenco area. This figure shows optical photomicrographs of samples. Top two samples are from Val Molenco. The top sample shows the serpentine content of 40%. Serpentine is shown as a blue color here. There are olivine and also some diopside and minor magnetite in it. Then this sample containing higher content of serpentine, 87%. And the bottom two samples are from Punta Retolina. The serpentine content here 93%. The bottom one has 18% magnetite in it. Then the lattice preferred orientation of serpentine was determined by EBSD. This is the result showing serpentine fabrics we found. The reference frame is X lineation, S for foliation. 001 axis is aligned subnormal to the foliation, which is quite consistent with the previous studies, experimental and also natural fabric. Here we found 010 axis is aligning parallel to lineation here as well in another sample also. Okay, using this fabric, I calculated the seismic anisotropy. As you can see here, P wave velocity was about 23% for sample containing 40% antigonite. The P wave velocity increased with the increasing serpentine content up to, I cannot read well, but it was about 35% for the serpentine, 93%. S wave anisotropy also increased similarly from the 23 to here 30, maybe 30. I cannot read well, but 33 or something like that, as I remember. More importantly, this is the plot showing polarization direction of a fast shear wave. This is a horizontal shear, and then flow direction is here X. Then we are looking down. Then you can see the flow normal component here. Also, the other sample also shows a similar trend. This seismic anisotropy produced by the serpentine can be used to explain the transparent seismic anisotropy. One more thing to consider is the effect of flow geometry on seismic anisotropy. Because when you have this subduction angle here, serpentine deformation could be, seismic signature of this future fabric would be different. So that I chose one sample containing 87% of serpentine. This is the sample which I already showed you, and then I picked up one sample showing a flow normal component for the set equal 0. For this is the horizontal shear, horizontal flow. And then when I increase the theta subduction angle 10 degree, there are still some flow normal component, but there are little things going on, a different orientation. When subduction angle becomes 30 degree, it becomes flow parallel. And then here 45 degree also flow parallel. But when subduction angle increased to a higher angle, flow normal components came back. Okay, so this data shows it depends on the subduction angle for the sample serpentinite deforming in this area. Okay, one more thing I considered was olivine fabric. What effect olivine has on the overall seismic anisotropy. I chose one sample here containing 52% olivine and then 40% serpentine in it. Olivine fabrics are shown here. Reference frame is same as before. 001 axis was aligning subnormal to foliation, and then 010 axis was aligned so parallel to lineation, which is a new fabric. I don't know yet. We need more investigation on it by experimental study. Anyway, using this fabric, I calculated seismic anisotropy. P-wave anisotropy was up to about 6% for the olivine. And Tigorite had an anisotropy here about 23%. By adding them together, I found the seismic anisotropy reduced to 10%. S-wave velocity anisotropy also reduced by adding olivine. Okay, now talk about some implications. This cartoon shows the two-dimensional corner flow material in the subduction zone. If we have a fabrics, same as the fabric which I found here, 010 axis will be aligning parallel to flow in this area. Then this can produce seismic anisotropy, even horizontal flow. Another thing, the serpentine wear here in this area, in between Mantle, wedge, and slab, the seismic anisotropy due to serpentine fabric will be dependent upon the subduction angle theta. Okay, more recently there was some more fabrics, serpentine fabrics reported by Nishi et al. Showing quite similar fabric as we found here. So one axis is aligned parallel to lineation. One more thing I'd like to show here is that this is a more recent data we are getting. We collected some more samples in a gold tree in Italy, here in this area, close to Genova. The field trip was guided by Marco Scambelleri, and then here's John Freeler, I think he was joining there and looking at it. We collected sample there. This is some work my student is looking at. He was finding there was one axis was aligning normal to foliation, and also the O axis is aligning parallel to lineation. This is quite consistent with the previous studies on the nature of serpentine fabric. In summary, lattice preferred orientation of serpentine was studied. Antiborite 001 axis line subnormal to foliation, and 010 axis line subparallel to lineation. Seismic anisotropy of shear wave was large, for example, 23 to 36% for samples containing antiborite volume fraction of 40 to 93%. LPOs of serpentine can be used to explain transparallel seismic anisotropy in a cold mantle wedge. Then seismic anisotropy caused by the LPO of serpentine also depends on flow geometry. Current data suggests that a strong transparallel seismic anisotropy with a delay time of up to 2 seconds in the cold fork mantle wedge can be attributed to LPO of serpentine. Thank you for your attention.
Thank you very much. I think we have time for questions.
Where did you say the cold wedge is?
Cold wedge. Where is the cold wedge? Yeah, can you show? Cold wedge.
Well, let's see. Let me go back here. Well, this area, I would say, I just draw this cartoon very terribly slow where serpentine is steep.
Sorry, I think you can understand. The patterns of the mantle flow matters to get like trench parallel anisotropy with serpentine, which has to be like trench perpendicular to flow or trench parallel to get trench parallel anisotropy.
Well, in the mantle wedge, in the mantle flow, if you have a serpentine, then it depends on how they are deforming. I just show here the subduction angle, for example. Then, depending on flow direction, then it would cause different seismic signatures. Okay, thank you.
Okay, thank you very much.